Well, my name is Michael Sarahan. I work for Anaconda, formerly Continuum. I'm on a packaging team. I've been there about 2 years. And I got into this mess because I got into Python as a scientist back when it was necessary to compile all the stuff to make it work. And that was really painful, but I got good at it, and now I have a job. So here we go. I'm going to teach you guys about all the stuff we have to contend with, and hopefully give you guys an idea of how to build your own packages and how to know what went wrong with packages you deal with in the wild. I'm going to talk about what a package is in a slightly more general terms than the talk yesterday on packaging. I'm going to try to cover some of the many things that'll break packages' compatibility with each other. And finally, I work a lot on tools that make that easier. One of the tools we work with is how to automate builds, because ultimately you can't make software all compatible with one another. You just have to build it for everything. So automation's a big thing. Probably won't get to that, but anyway. So you want to make a package. What is a package? In a broad sense, it's anything you install using a package manager. Conda is one such package manager. You've got Yum, apt-get, Chocolatey, all these things. Pip is a package manager. The key thing about it is that each different kind of package may have some kind of implied behavior to it. And so like a wheel is a Python-specific package thing that's intended to be installed by pip. Conda packages have some implicit behavior we'll talk about later about how they're arranged and what that, well, Conda really depends on that arrangement to make it work. There is an unfortunate overloading of this namespace you should be aware of. Python talks about packages as a folder that you can import. I'm not talking about those at all, okay? So as far as file types in the wild, you might see with Python, you've got sdis, and those are just source stuff. A long time ago, people made this thing called eggs, and they were just zip files, and you could directly import them, and they didn't end up working out very well with binaries. And so with binary dependencies, which is especially critical in the scientific space, you kind of had these two other offshoots, wheels and Conda packages. They came out about the same time, 2012-ish. They're both effectively zip files. Neither of them are meant to be directly importable, and there's some important differences between the two that we will cover a little later. So wheels versus Conda packages. Wheels are kind of the official solution you'll hear about from PyPA. They are increasingly available for all the numeric scientific stuff you might need these days. So NumPy, SciPy, scikit-learn, these are all getting wheels. But they have some really important differences that make me prefer Conda packages to them. So, so relative to Conda packages, they're less general purpose. They must contain or statically link any of their binary dependencies. And one thing that's much better about them is you can say that, oh, this wheel is compatible with Python 2.7, 3.3, 3.4, but not above, or something like that. Conda packages kind of stink in that regard right now. We're working on that. Where can you use wheels or Conda packages? You can use wheels anywhere. So if you're using Anaconda, you can pip install a wheel. That's fine. There's stuff you need to be careful about because pip is not always aware of files that are managed by Conda. This is a very general problem with having different package managers in the same space, right? So they each want their notion of what is, and if they aren't collaborating with one another, they can step on each other pretty easily and make a mess. So you can certainly use wheels in Conda environments, but you need to be a little bit careful about it. You can't use Conda packages with pip, virtualenv, venv, etc., to the best of my knowledge. So here comes some interactive stuff. Who went to Stephen Cutting's talk yesterday? A few people. So he went through a really, really great manual process of doing all the steps to create a setup.py and a package. I don't do any of that. I don't have time to do any of that. What I really recommend is Cookie Cutter. And this is a really fantastic project. Oh, seriously? GitHub is down? That's unbelievably bad. My internet's garbage. The internet's down! Yeah. Well, dang. Anyway, what Cookie Cutter is it's I think it uses Jinja 2 as a templating engine. and people define their own project templates, and you clone that repo as a project template, and then you put in a few bits of data, and it fills in like the name of the project, your name, your contact info, where the repo is, all this stuff. And what comes out is something that's already nicely laid out for you. So I love Cookie Cutter. The other nice thing about Cookie Cutter is there's a lot of different templates for whatever different kind of project you have. So if you're doing Django, there's a Django template. There's ones that have different test suites, whether you want Nose or PyTest or whatever. They have them set up for the different CI services, so Travis CI, AppVeyor, whatnot. You can mix and match, make your own template. This is one we have for Conda. And unfortunately, I'm not sure that my example here is going to work. So for those of you who did the Docker stuff, or you already have Miniconda installed, what I'm going to recommend you do is, just take a look, say, yep, Conda's working. And I am going to install Cookie Cutter, hopefully from Conda Forge. Nope. This is so sad.
Open up a non-secure page, and it should redirect to get you in full access.
Oh, that's a good point. Purple, do you guys know about purple.com? It used to be a really nice, just like purple color background that somebody had sort of stomped on the domain name, and they sold it.
No, you didn't finish.
That used to be my go-to. What?
You didn't do enough.
Okay.
Do the tab in.
Well.
Google security and non-secure. Go to HTML5
HTML5 what?
ZOMBO.com.
There we go.
Close enough. Upper right in the gray. They had it. Now you're in.
Sweet, thank you. And we're off to the races here. So what this conda install command is it's a lot like pip. It's going out and it's going to get a package. The -c is getting it from a channel. We'll talk more about what a channel is. This particular channel is Conda Forge, which is a community of a lot of different packages. And what we're going to see is going to bring in all the different dependencies. And I'm going to say, yep, please. And now I have this cookie cutter binary that takes in a template, right? So I'm going to go back to my presentation and paste in this URL. And I will go slow here so you guys can catch up. Blah. And so you guys who went to Stephen Cutting's talk, you'll recognize that some of this stuff this is the outer folder, his repository name, and the inner folder, the package name by default matches. This is package in the Python folder sense of the word. And what this has created for me is this blah folder, name of my project, with all that layout. And if we look at setup.py, nice, yeah.
A little too fast.
Yeah.
No. Good.
I'm just watching and it's hard to read. Is there a
What? Too small?
No, too fast.
Too fast. Great. Thank you for the feedback. So let me just leave my console up here.
10 seconds.
You guys can catch up for a bit.
Is there a stuff at the very top? Stuff where the like
Yep.
Docker kind of board and all that kind of stuff?
Yeah, so when you first got cookie cutter in, thank you.
There you go.
Oh, that's how you got it.
At least I'm not clearing my console. Yeah.
Barely 10 minutes in. Barely.
Bad habit. What you see here over on the left is a good example of some of the ways that Conda is handling that, what I mentioned about different versions of Python that packages are compatible with. So for a long time, Conda really only supported a single Python version in a given package. And the reason why it did that was that it was compiling all the Python code to bytecode, and bytecode's not portable across different Python versions.
Is this on live?
There's a recording of this talk.
No, you keep going back and forth and stuff.
Well, so at this point, I'm kind of at the top of the talk here. So take a look at Conda installed. If you need the Docker command, I can move that up too.
I don't think I got that.
You don't need Docker. If you've already got Anaconda installed, you can just run Conda commands on your own system. That's fine too. A little bit. But what I'm pointing out here is this one, this py underscore, has no Python version associated with it. It's what I referred to as a no-arch package, and it's handled differently. It doesn't embed the PyC files at build time. It actually leaves them to be generated at runtime, which is what makes that work. But we still kind of are lacking in a nice syntactic way of saying, oh, this is only Python 3, right? So there's room for improvement here. Conda-forge. You ready to move on a little bit? So let's go down to the cookie cutter command, and y'all type this in. What this is going and getting is just a cookie cutter template that we created for Conda packages. So it's nothing unique or special. It's just a slightly different template that includes different initial files for you. And the reason why we created this one for Conda is to include some of the files that you use to make a Conda package. And so the kind of the community standard is that these live in a folder called Conda recipe. And this is the input to a program called Conda-build. We'll talk a little bit more about later. It lists the requirements for that package, both at build, run, probably test time too, how to install it, and this ends up as that .tar.pz2 file that I talked about earlier. So if you were to go and get other cookie cutter templates, you know, they may not have that stuff. Cookie cutter data science. This looks like something else. Rats. Go with what you know. So one of the coolest things about this cookie cutter repo is cookie cutter itself, but it's also this big collection of cookie cutters for all the different kinds of projects you can create. It's not just for Python, right? You got C, C++, lots and lots of different good stuff in there. So if nothing else, you can look at these examples and take bits and pieces out of them and make your own, should you so desire. Okay, who's ready? Hooray, lots of people are ready. So, okay, what we have in this blah folder is basically like your Python project. And it's, when I start a new project, if I've already got code I'm working on and I just need to make it kind of like packageable, I'll still use cookie cutter to make this template, and then I'll copy my code into that source tree. And it's just to save you the time of figuring out what that source tree should be and doing all that boilerplate junk. But now that we have this project, you can do all the different commands to set it up and run it. And so you guys have seen a lot of Python setup.py commands, right? If you say Python setup.py install, that's going to go ahead and install it. You could do Python setup.py develop. What this does is rather than copying the files into your Python source tree, it's putting in like a link. And that link is nice because you can hack on your code. And when you kind of like reload Python or reload the module, it'll reflect your changes. Very, very powerful development tool. You can also say Python setup.py bdist wheel. And that's the command to output a wheel, right? And I believe it puts it into this, where did it go? Build, bdist. Yeah, here it is. There's my wheel. Cool, right? Didn't take long at all to get us a wheel. All right. Now, because we also used a template that included this Conda recipe, we can build a Conda package. By default, Conda or mini Conda does not include Conda-build. So if we just say Conda install Conda-build, that's going to go out to the different repositories that Conda is configured for. Go get Conda-build. And if we tell Conda-build to build this whole folder, it's going to process that meta.yaml file and spit out the .tar.bz2 file. Okay, so what Conda-build is, I'll go back to the slides here in a second, so if you guys are following along code, let me know when you're ready. What Conda-build is a tiny bit more than like bdist wheel. What it's doing is it's creating Conda environments for both the build, the run, test phases, all these different things, and it's taking advantage of Conda's environment isolation at every different step. So what you saw there was a bunch of package installs. That's setting up the build environment. So these satisfy whatever the requirements were. If you remember, the requirements were only just Python and setup tools. So almost everything you see there is a dependency that's being brought in. And then you see it's running Python setup.py install there. We end up with 12 files in the package. And this package now exists locally on our computer. And if you so desire, you can upload it to anaconda.org, our package hosting service. I'll talk a little bit more about what the details are there. Everybody who wants to run.
Could you just type history?
Yeah.
There you go. Good idea. Conda-build, the fact that I passed dot there just means Conda-build this folder. And what Conda-build does is it goes and looks through all your folders and says, well, do you have any meta.yaml files in there? If you do, I'm going to find them, and those are what I'm going to build. If you have more than one meta.yaml file, it's ambiguous, and it's going to barf and say, you got to tell me which one. You got to specify which folder you actually want to build. But all right, we ready? I'm going to go talk some more. So we've seen cookie cutter. We talked a tiny bit about what makes up a Conda recipe or a Conda package. Relative to a wheel, Conda packages are language agnostic. We are not tied to Python. We have R packages, Perl packages, all this different stuff. The really, really key idea to get about Conda packages is that we have this folder structure within the package that imitates a Unix file system layout. So what we imitate is the /usr folder. And so you'll see like a bin folder, potentially an etc folder, share, lib, include, all these different folders. And with that relative path stuff, we're able to do like relocatability, meaning you can build your package in one location, and we do tricks to make it installable then on anybody else's computer, any other location, even though there may be hard-coded paths in there. And it's all based around this file structure. So this is kind of the interface that a Conda package presents. And all Conda-build is a massive bunch of helper scripts to orchestrate environment creation and isolation, and also manage all the metadata that tells Conda about your requirements and what it was built with and what files are in it. Lots and lots of data there. So we've seen how Conda-build works. There's also a really, really nice tool called Conda-skeleton. And what this is for is a lot of the time you're not writing a brand new project, right? You just want to bring something else that exists into the Conda ecosystem. And there is a tool called Conda-skeleton for that. It's part of Conda. So what this works is you pointed at the repository that you want to go grab the thing from, say PyPy. We have bad mic luck today.
I didn't bring these mics, so I'm just fixing them.
That's good. Thank you for fixing them. And so I'm going to pick a package that I know works here, Beautiful Soup. And so this is going to go out to PyPI and take a look at what the package metadata is that PyPI presents, and then reinterpret that, cram it into a meta.yaml file. And so if we say ls, what you'll see is I've got this new Beautiful Soup folder. And this just has a meta.yaml file in it. And in this meta.yaml file is Jinja 2 stuff up at the top. So that's setting variables that are going to get templated into other places in the file. And that's mostly to make it it makes it nicer to maintain, because any of the editing you do to keep this up over time is only at the top of the file. You don't have to do this like crazy search and replace to find the values deeper in the file. So you see it says it's got the package name, what the version of the package is, where to get the source code for that package, how to verify that the source came in and is accurate, how that it is what you think it is. So hash some validation, all that good stuff. And then you got this is kind of like extra data that says how to build it. It can exist in different files if it's more involved than this. Build numbers are kind of what we use to say, look, the source code didn't change, but the way I built it did. So that's like our differentiator for when you've changed what the package might contain, but not the version of it. And finally, you got a whole bunch of metadata that talks about what the package is. Okay, so just the same. Yeah.
Why wasn't the build number a variable?
It certainly could be. You know, anything can be a variable. Most of the time, you do. It depends how much work a recipe takes to be developed. And so what I'm going to show you here is, I'll show you the Python package is one that we've iterated on a ton, especially recently. We switched over to a brand new build infrastructure, new compilers and things. And so what you'll see is we're up to build number 23 because we've edited that recipe a lot, different times. But most of the time, once you've kind of like zeroed in on what the recipe is, you don't generally bump the build number. You don't edit the recipe. You bump the version number, at which point you reset the build number, and life goes on. So it's really a question of like how actively developed a recipe needs to be. And ideally, the answer is not, right? Ideally, your recipe stays the same over time and just keeps working. Fingers crossed. You know, you always hope that your upstreams don't change things on you. So that's really why I'd say that the build number is typically just left there, not templated as a variable. It's also a matter of it's not something that gets reused elsewhere in the recipe. So the version and the package name and other things like that will get reused in several places throughout the recipe. And putting them in as a variable makes it easier to make changes throughout. All right, boy, I am running out of time. 15 minutes. Huh? 25, really? Okay, cool. So this was like a kind of deceptively simple, because what you just saw worked wonderfully, and it didn't include any dependencies, it didn't include any binaries, we didn't inject any kind of dependency versions. So this is just to show you kind of like the guts of it. And now I'm going to talk about like how things get a little bit more complicated. I guess before that, I want to talk a tiny bit about package hosting. So the two main ones that I would advertise, PyPI, we all know and love. PyPI is an incredible resource, even more incredible based on the talk we heard last. It's totally centralized, and this is both a strength and a flaw. What it means is that there's only one provider of the NumPy package, and it has very well-determined compatibility bounds, but those compatibility bounds might not be the same as some other package, right? So by having many different maintainers in a global ecosystem space, the demands to keep things self-consistent and compatible is a lot harder. Anaconda.org is Continuum's or Anaconda's site for community hosting of packages. Anybody can host packages on their own channel. Every channel has its own packages. They can all be totally self-consistent. So it's a different model. They're both totally free. What I think you might find is that a lot of the scientific ecosystem has arranged on anaconda.org because it's easier to keep their ecosystems self-consistent. And the wheels situation is kind of catching up, but you're seeing a lot of growing pains with the wheels where people are not always respecting the standards for what the binary compatibility bounds are, and then you get packages that just don't work where you expect them to work. All right, so to talk a tiny bit, the big thing about going up against PyPI is that PyPI has been the central repository forever, right? It's got more than 100,000 packages. That's pretty hard to compete with. As Travis said, you don't need 100,000 packages. I've got crap I wrote in grad school on PyPI, right? And there's no way anybody's ever going to install it because it was crap. But what we have on anaconda.org is generally the core, really incredibly useful thing, really incredibly useful stuff. And this is focused based on communities. So we've got different organizations that have bonded together to put stuff on anaconda.org with their own build systems. Bioconda is bioinformatics stuff. Omnia is molecular dynamics. Menpo is computer vision. There's a lot more. More generally, you guys remember CondaForge was the channel we used to install Cookie Cutter from, right? That is a community effort. Anybody can submit a recipe. It gets built by CI infrastructure, so Travis CI, AppVeyor, Circle CI, and it currently has about 3,500 packages. I gave this talk, a close relative of this talk, in June or July. Back then, that number was about 2,500. So it's growing really, really fast. So now let me talk about the different ways that things break. Who has ever written a program and then updated the software that that program was written against, and all of a sudden it doesn't work anymore? Yeah. So that's what you call an API breakage, right? It's when the interface, the programming interface to that program has broken. Happens for any number of reasons. They change the order of the arguments, the type of the arguments, lots of different ways for this to break. ABI is something that happens because you've used different tools to compile it. And so like different GCC versions, different Microsoft compiler versions, things like that change at the ABI level. You'll also see ABI changes when they've changed like low-level stuff that you compile against and link against, right? You can see breakage at that level. Pinning and constraints is another way that people break stuff, but it's also a way that we compensate for stuff being broken. I'm not going to talk about API or ABI anymore because they're just too complicated for this talk. Just to say that patching, pinning, and constraining are the Swiss Army knife of a package builder. This is how you need to spend your time figuring out how to keep your package working. And so you need to study what your dependencies are and say what your bounds of compatibility are. And that's, if you do it carefully, you keep your package working. And if you don't do it carefully, you end up kind of making your package incompatible with other stuff. So what I would advise you to think about whenever you are coming up with constraints, keep it in your head. Are you creating a package or are you creating an environment? And I think this is the source of a lot of confusion from people who put stuff up on PyPI. They put up a requirements.txt file that's pinned very specifically to many versions. And that makes that package very hard to install with other packages, right? Because those versions are, it's easy, if two things are too specifically pinned, it's easy for them to be incompatible. It's easy for them to not line up, right? So what I would say is if you constrain tightly for an environment, totally fine, right? Email your requirements.txt file around and use it. That's great. Don't put it in setup.py. Don't put tight constraints in setup.py. So a lot of people think requirements.txt, setup.py are equivalent. They're not. Requirements.txt is for environments, setup.py for the package. Okay, why do things break if they're too tight or not tight enough? If they're too tight, it means that upstream developers, they change code. Well, it doesn't break your users, but you have to rebuild your package in order to support that new code because your constraint's too tight. Otherwise, pip does not have a dependency solver like Conda does, so this is kind of behavior difference in the two worlds. But basically, if package A in this is pinned to 1.0 and over here is pinned to 2.0, how do you resolve that? And that plays out in different ways between Conda and pip. In pip, the last one in wins. And in Conda, you'll say it's unsatisfiable. Can't even do it. Throw up your hands and fail. If you're not tight enough, what you risk is, like many of you have experienced, the code changes and your code no longer works, right? So I talked a tiny bit about this. Pip has an outstanding issue to put in a dependency resolver. I don't know what the current state of this is right now, but the behavior is kind of scary for a top-level requirement, meaning one that the package itself specifies. You can only allow that one spec per project, otherwise you duplicate the requirement. It does throw an error there. And they override any of the dependencies lower in the stack. Yeah, it's scary. And then for sub-dependencies, first found wins. And breadth first search means you've got your dependency tree and you're kind of going through that. Yeah, so pip's dependency behavior is kind of scary, and it's really remarkable that anything works at all. But it does, and that's the important part. Conda and Conda-build, because Conda-build uses Conda, it does have a satisfiability solver, and it'll just simply die on you. And this is also very frustrating behavior. So rather than stuff kind of ceasing to work at install time, it'll cease to let you install things that are incompatible. And that can be very frustrating to users. We field a lot of questions on users confused as to why a package that was only built for Python 2.6 is no longer available to them, right? Okay, how do we help avoid breakage? And I promise we'll get to more interactivity. Well, maybe. We can control a few things in our ecosystem. We can't control the API. We take what we're given from upstream. We can control the ABI by controlling what tools we use to build things, and we can certainly control constraints. So as far as ABI compatibility goes, there's no like crazy technical trick to this. You just define what your tool sets are, and you say, hey, everybody needs to conform to this. these are our tools. As long as you build with these, our compatibility is well understood in this space. This is something we're trying to get Conda Forge on board with, is building with all of our same compilers that we use at Anaconda. It's a social problem. It's not a technical problem. Getting everybody on the same page, and also making sure that that tool chain supports all the features that everybody wants to use. So C++ 11 and 14 are pretty new, and what we've done in the past to keep compatibility on Linux is to build with really old compilers. Okay, well that doesn't support C++ 11 and 14. So we now have to figure out a new process to support these things, and it's challenging. It's a social and a technical issue, I guess. I talked a little bit about the channel model of anaconda.org being better than PyPy because it allows each channel to be self-consistent with regards to API. The downside of that is that mixing channels really, really hurts. And that's a major downfall of that system. By analog, PyPI relies on community standards such as Many Linux 1. It says, okay, well, you have to build on CentOS 5 with this compiler. But people aren't actually restricted to doing that. And so who here has used TensorFlow on, say, CentOS 6? Forget it. Nobody has because it doesn't work. They build it on a Ubuntu 16.04 machine, and that establishes their lower bound of compatibility, even though the Many Linux 1 spec says you need to build on CentOS 5. The reason why they do that is it doesn't work on CentOS 5. You can't compile it, right? They've used too new of a language feature to make it work. So, so PyPI is incredibly, I really commend them for trying to establish the community standards, but I think they need to do a better job of enforcing it. Or have a better way of communicating what the exact bounds are, at least. All right, I'm going to skip over this. We track a lot of metadata to try to keep things compatible and know where they're compatible. And this is info that we kind of provide to Conda for you to be able to specify what you want. Okay, general advice, avoid constraints as much as possible. Keep your recipes as general as possible. And use tools to fill in constraints where necessary. So Conda-build 3 came out in July. It uses Jinja 2 and a lot of fancy tricks to do a lot of this dynamic pinning behavior. And I want to just whirl through a real quick demo to show you guys some of the dynamic stuff that this does. This is the basis of a blog post that I'll give you guys a link to at the end. But fundamentally, what we're going to do is we're going to use Conda-build's Python API. We're going to write a function to render the recipes, which takes meta.yaml in its template form, and stick in whatever variables are there and get it into a final form, print out what's there. And we're also going to use an API function to say what files are going to be produced. And so what this is going to show you is the different like Python versions that might go into something, or different varieties of things. So this general templating scheme, one of the coolest things we did here was we took arbitrary values that you can put in meta.yaml and put that configuration outside. So you can now have a centralized version pinning thing elsewhere in your system that controls a lot of other things. And so here we're going to say something. We have two values for something. And what we get out there when it's all said and done is, well, Conda-build's telling us, hey, I can't install that something package. It doesn't exist. Cool, helpful information, right? We get two files out because we had two different kinds of dependencies there. Something 1.0, something 2.0. Okay, we can do the same thing with Python versions. And what you see is Conda-build is what I call finalizing the recipe. It's freezing in all of the build dependencies that were used there. And part of this is for reproducibility, because unless you know exactly what you built with, you don't know how you got there. Got a couple of different recipes. We also do some neat stuff regarding compilers. Again, sorry I'm skipping over this. Check out the blog post. There's just not time. What we specify in Conda recipes is not so much that you have to use a particular compiler. What we specify instead is you need a C compiler, and we don't care what it is, That's part of external configuration. And what this frees us up to do is do some really, really neat potential cross-compiling. Thank you. And this makes it easier also to support all kinds of different compiler flags. So we build almost all of our software for ancient CPUs for the sake of compatibility. SSC3 goes back to like 2006. If you wanted to build something that was for modern CPUs, AVX2, that kind of stuff, you could just have a different compiler configuration that mapped to one of these names, and then you're off to the races. So finally, the major innovation, the other major innovation for Conda-build 3 is that rather than have the dependencies always be defined downstream, as far downstream as you can, like on the package, right? Instead, you should know, based on what's present at build time, what also needs to be there at build time, or runtime, sorry. And this is really centered around a lot of the shared libraries. And this gets into the ABI-specific behavior. So you know with what you built where your compatibility bounds are. This is totally a per library knowledge. And the trick here is that rather than having that pinning, that constraint, be something you have to apply across every different end recipe that uses that thing, you pin it upstream and it applies downstream. So here we go. bzip2 is compatible, and we're going to build the recipes that use that. And what we end up with is this second recipe does not list bzip2 as a dependency at all, right? It rather uses a different package that is saying, whenever you build with me, you have to add a runtime dependency. And what we get out is it has added that new runtime dependency for you. So this is a great way for newbies who often forget these kinds of things to not forget them, right? The experts define it at the top of the stack. Everything comes out of the bottom okay. Okay, Conda-build 3 is fun. And I'm just about done here. Build matrices, flexible compilers. Yeah, this is my team at Anaconda. They're awesome. They're a bunch of wizards. And there's a couple of blog posts I can send you guys links to if you like. And I'm happy to take any questions you guys have on this mess. Yeah. Absolutely. So there's this thing called Anaconda Enterprise, which actually Anaconda.org is an instance of. And so if you really want to host your own packages, it's a way to do that. It'll host PyPI, like wheel packages. It'll also host Conda packages in private ways as much as you want. That allows people to kind of like control versions in a better way and say, for my enterprise, these are the versions we're going to support, and these are the software sources we're going to support. Yeah.
So I noticed that BioConda and Conda-Forge seem to have very different styles about their recipes. Is there a best practice for how these things should play out?
Well, there's a best practice on a per community basis. And what I would say is the general movement of the whole community, everybody's unifying at Conda-Forge. And so Conda-Forge may adapt some of BioConda's preferences, and BioConda is probably going to adapt some of Conda-Forge's preferences. And we'll all have to compromise to find something that works for everybody. Sorry. The question was, there's a difference between BioConda and Conda-Forge recipes. Is there any way of standardizing the community on that? The answer is yes, through arduous, persistent attendance of meetings and pushing for your way and compromising. Cool. Yeah.
So you talked a little bit about building these dependencies as the conda-builder knows. How does that relate to your talk earlier about change dependencies? Because it seems like that was pretty strict. Like what was your build time?
No. So it doesn't strictly become the depend. So let me show you, I guess. I'll go back to this and show you the finalized recipe is not so much that it becomes the runtime dependency. The runtime dependency is flexibly defined based on whatever the build time dependency is. And so the default behavior is to match the lower bound as whatever's present at build time, and to have the upper bound be the next major version. So it's a total assumption of semantic versioning. It's customizable though. You can also say max pin equals x.x, and that's a syntax that says pin major and minor. So at that point, it'll be the same major version and the next minor version up. You can also say x.x.x, right? Bug fix version. So that's totally customizable, but the really cool, neat, new thing about it is that it's dynamically determined by whatever the build version is that's present. And that dynamic behavior has been what's hard to maintain in the past, because when you want to bump your versions across your whole system, you edit everything, right? Here, it doesn't matter. You just rebuild it. You update one package, and as long as your constraints are then going to use that new package, everything, you just rebuild it, done. Okay. Well, if you're interested in how we automate this, we use something called Concourse. And we use Concourse because it's able to submit dynamic jobs. They're all text-based, and so we can generate them on the fly from other jobs and resubmit them to feed the system. Kind of looks like this. It's pretty. It makes really big dependency graphs. This is, well, looks like this is only one OS, but like 5 or 6 different packages. It builds them in order, figures out the nice tree. It's fun to watch. It looks like a Christmas tree, and it makes our lives better.